Hello, viewers. My name is Andrew Dean. I'm the Vice President of Research and Innovation at Lakehead University, inviting you to an edition of Research Matters. So today we're really excited to meet Dr. Ahmed Elshaer, an assistant professor in the Department of Civil Engineering at Lakehead. Associate, I thought it was associate. Sorry about that. Associate professor in the Department of Civil Engineering at Lakehead University. So welcome, Ahmed.
Yeah,
we're really pleased to have you join us today. And maybe just as a bit of a opening, can you tell us a little bit about your educational background and how you found yourself to Lakehead University?
Sure. Thanks, Andy, for having me today. I'm Ahmed Elshaer. I started my academic career having my bachelor and master's both from Cairo University in Egypt. And after that, I moved to Canada, where I got both my PhD and postdoctoral fellowship at Western University. And then I moved to Thunder Bay, where I established my research group here at Lakehead University. I named it SWERL. It is an abbreviation for Structural and Wind Engineering Research Laboratory, and it's kind of inspired of the swirling motion of wind and vortices. And we have some research directions, and our research group now is having 7 PhD students and 5 master students and around 7 undergraduate research students.
Wow, it's quite impressive for such a short period of time, actually. Yeah. And I must admit, the SWERL sounds like a wonderful name for it, okay? It's easy to remember and comes quickly to what it's all about, actually, as well.
That's true.
That's good, okay. So tell us a little bit more about the types of experimental testing that you do in your lab.
Okay, so if we look at the research directions that we currently have, it is kind of divided into between 3 or 4 categories. So the first category is related to structural performance. So we look at how structures actually perform under natural hazards. One of the strategic projects that we currently have is looking at indigenous housing and how we can tackle this interesting problem. Because typically indigenous regions are characterized with severe wind load as well as snow load. And if we look at even at climate change, you'll find that Canada is actually having impacted by climate change at double the global rate, and indigenous Canada or northern Canada is impacted with 3 times the global rate, which is quite interesting. So we kind of have a full framework for how to tackle this problem, starting from identifying the climate impact and preparing the structures to resist this type of load, and also creating some structural solutions to resist those types of loads. So this is more or less the first type of research work that we have. After that, we have the impact of extreme temperatures, and we look at both sides of the extreme temperatures. So we look at extreme cold temperature, which can be found in northern Canada, and also we look at the extreme warm temperature, or even specifically fire hazard. So we look at both sides. I have one of my master student, Kendra, is working on that side of the project, and Amir Ali is working on the project related to the cold climate. And the third type of loading, or the third type of research that we have here, is the impact or the wind load evaluation for structures. So we use some optimization and AI-inspired techniques in order to perform our numerical analysis and look how to integrate those AI. We live in the world of AI currently, so we found it very handy to map properties between what we found in real physics and how we can map this with numerical models.
Okay. I mean, we hear so often about the problems and the shortage of housing for especially in indigenous communities, and sometimes we think it's just a matter of well, just get them built or something like that. But you're absolutely right. I mean, the environments that we live in northwestern Ontario are quite harsh. So you want these to last more than 1 or 2 years. So you really have to take that into account. Our environment, the speed that you want houses to be built at, the number of people occupying a place, the ground, all those kind of things, I'm sure, right?
Yeah, you are absolutely right. Like the weather that we currently have is very special. Like if we look at like the design wind load, if we look at level of design load, let's say, or design wind load in terms of Toronto, for example, this we usually measure it with something called return period. So for the same magnitude of return period, we find that this design wind load can be found every 50 years. But in northern Canada, it happens every 3 years. So this is kind of reflection of how risky the climate in northern Canada. And also if we look at the difficulty in transportation, so majority of the transportation rely on winter roads, and this will require like some lightweight type of structures so we can move the construction materials to the location where they will be deployed, and they have to be kind of lightweight as well as not like constructed like even we thought about the modular structure in terms of volumetric modular structure, but the problem with this that with the winter roads they will deteriorate while transporting them. So this is what we came up with the idea, and actually I have one PhD student who's working on that idea, named Mustafa Al-Hadari. He's working on that by creating what we call it panelized modules. So those panelized modules, they are, I like to describe them that like a build-it-yourself type of structure. So once they are transported to the location where we look at our deploying our modules, our modular structures, they can be assembled with long bolts and then deployed at this very location.
And of course, with so many things in northwestern Ontario, and certainly remote communities, I mean, pretty much everything has to be brought in. You know, I mean, it's one thing to build a stone house or a brick house in southern Ontario, but we don't have the supply chain up here. We need to make sure that whatever we're bringing in can be brought in, can survive that transportation, as you say, and then actually survive our weather as well.
Absolutely, and it is not only transportation. It's, let's say that we solve the problem of transportation, then the problem of having heavy machinery at this location and also skilled worker to deploy those structures. And what about repairing those type of structures? Like majority of our structures, let's say if we have like a steel structure or a timber structure, sometimes they get through some sort of renovation or repair if damage happen. This thing becomes much more harsher when it comes to remote communities, because we need it to last long at those very remote regions. Otherwise, like it defeats our purpose.
So you mentioned a little bit about numerical simulation and AI and how this is maybe doing some of the basic lab bench work, kind of work before actually going to structures. Tell us a little bit more about that.
Okay, so when it comes to numerical simulation, actually we can have like a number of them so far. So if we look at first the simulation of wind itself, the state of the art currently is conducting what we call wind tunnel testing. And I don't want to steal Raghdah's thunder about wind tunnel testing. So, but simply it is a tunnel where you simulate how the structure will perform under a hurricane, let's say. But this, as much as it provides like a very accurate result on how the structure will perform within those extreme climates, but the replicability of this approach sometimes be challenging, especially when you are trying to do it in a city scale, or if you are trying to test different alternatives. Like one experimental testing could cost easily $20,000, and let's say if we are building multiple houses and stuff, it would become very challenging. So what we alternatively do is we do what we call computational fluid dynamics. So our lab work on improving those type of numerical simulations, how to pick the right type of simulation, the inflow boundary condition, and all those details. Also about the numerical simulation, we have what we call it finite element analysis. So how we can simulate the behavior of the structure itself, but mathematically. And even with those numerical simulations, sometimes they can become computationally expensive. So in order to map those behaviors, we adopt what we call it surrogate model. So those surrogate models, these are the AI-based, or where we actually adopt some models like the artificial neural network or something like that, so we can predict what will be the behavior, but using the AI analysis. And here is where the quantum computing approach actually becomes very handy.
Wow, that's great. So thank you for introducing us to our research. We're going to take a short break and be right back to continue our discussions with Ahmed and a few of the students as well.
Thank you so much.
Okay. Welcome back. You're watching Research Matters, brought to you by Lakehead University. Before the break, we learned about some of the interesting research projects taking place in Dr. Ahmed Elshaer's research lab. Now we're going to meet two of his PhD students who will share more about the specific projects that they're working on. So welcome, Raghdah and Tristen, and we're really pleased to have you here today. So we'll start off with you, Raghdah. You've got a nice prop there as well. Could you please introduce yourself and just share with your viewers some of your educational background and your journey to Lakehead University?
Thank you so much, Dr. Dean, for having us here today. So I'm currently pursuing a PhD in civil engineering at Lakehead University. But way before that, I have acquired my 2 undergrad degrees one from back home in Iraq, civil engineering, and another undergrad degree in civil engineering from University of Salford in UK. I've also acquired the Master of Philosophy degree from the University of Manchester in UK, and we used to live there and then moved to the beautiful Thunder Bay in 2016 with my husband, our 3 kids. That's where after I've joined, became a member of the Professional Engineer of Ontario, and I have a status of like engineering training status. And then, continue further enhancing my further education with a PhD degree, which is focused on enhancing the the accuracy of wind load evaluation on low-rise buildings, as well as bring a design or robust aerodynamic mitigation techniques using both approaches, experimental and numerical. That's currently just to help increase and enhance the resilience of buildings in wind-prone regions.
Okay, that's great. I used to live in Manchester as well. Okay. So, as you said, you're studying wind pressure. Can you tell us a little bit more about that? You have a wonderful looking prop there.
Yes. It's really an important aspect to study and understand about the wind pressure, as well as this distribution of the pressure on the entire building surfaces from roof to wall. This will give us an idea about the forces that these surfaces will face during wind events. Some of the locations on the building will be more prone to be dislocated and hence initiate the chain of damages during the wind event. So my approach in my study is basically initiate and create that large database using numerical simulations, and have models like a low-rise building residential, mainly models simulated using simulated numerically, and then using different terrain. So we will simulate mimicking terrains that we like real-life terrains, such as suburban or urban terrains, and then add aerodynamic mitigation technique. And by that, for example, one of these modification technique that I've added to this low-rise building, residential building, is called parapets. So basically, what are these do? They mitigate, or they really displace the wind away from the edges. And then the most efficient best performing design will be then tested using wind tunnel testing. And by that, we actually create this print at Lakehead University facility, 3D print the model, mimicking all the parameters, all the geometrical configuration characteristics of the building that mimics a real residential building, from roof slope to all the other elements. And then we add these pressure tubes to the building, and the resolution, the number of pressure tubes will give us a real idea about the pressure and the wind-induced forces on the roof. Basically, what happened during wind tunnel testing after we prepare the whole numerical model is that we place it on a turntable, and so we can simulate and have that pressure values, magnitude, and distribution throughout all wind angle of attack. And then these tubes will be connected to pressure sensors, and that's where we collect the pressure data that's really give us a real-time pressure data. So by combining both approaches, numerical and experimental approaches, we are aiming to cross-validate our numerical model, our simulations, which will give us more accuracy to the results that we are producing, and hence hopefully to bring up a new design, robust design for low-rise buildings, so we mitigate and produce designs that are more safe and more wind resilience in region or within regions that are more prone to wind events.
I think that's one of the fascinating things about civil engineering that maybe a lot of people don't understand is, how much is actually done before structures go up.
Oh, yeah.
Whether it's on paper to begin with the ideas and the numerical calculations and the computer simulations, to prototype development,
Absolutely.
to then actually putting something into the field, and how much that actually can tell you whether it's going to work or not, and how that modeling has gotten better and better over time.
Absolutely. It's a long process, and we learn throughout each process, and to come up with an efficient design is not easy. Each of these elements that we add on the building is in fact like a lot of study and research gone for it. But hoping to influence the building codes, construction companies for a better and safer communities.
That's great, thanks. So I'm going to turn to you, Tristen, now. Can you please introduce yourself and do the same sort of thing? Tell us your educational background, how you got here.
Yeah, absolutely. So my name is Tristen Brown. I am a PhD candidate under the supervision of Dr. Ahmed Elshaer at Lakehead University in the Civil Engineering Department. I'm from Sturgeon Lake Cree Nation, which is Treaty 8 in northern Alberta. And I started my academic career at Lethbridge College, and I completed my civil engineer technologist diploma. And then luckily, Lakehead offered a diploma to degree transfer in the civil engineering department, so I took on that role and started my degree in 2018 and completed that in 2020. With first-class standings, and I got approached from Dr. Elshaer in my undergrad to do some summer research, so I did in the summer of 2019, and he was more than happy to offer me a master's position in civil engineering at Lakehead in start of 2021, and I've completed that in 2022, and now doing my PhD under his supervision for Indigenous housing.
Also Banting?
Vanier Scholar.
Vanier, sorry.
Yeah,
Okay, yeah.
Absolutely.
Tell us a bit about the Vanier Scholarship. It's wonderful.
Yeah, it's very prestigious. They offer 66 out of 155, or offer 66 out of 168, I think, each year for 3 consecutive years, and it's a $50,000 scholarship that. It's very rewarding when you get it, but it took a long time for that application, and clearly that the topic that I'm studying is well deserved for the field of engineering, and specifically it's great to be one of the only holders here at Lakehead, especially being an Indigenous research student. So I'm more than pleased to have that under my name. So yeah.
That's wonderful. I think quite often the viewers, they especially when they get a chance to meet with students or postdocs, it's really inspiring to see how the different pathways from students come to here at Lakehead, and then they carry on with their career, and what is this opening up, and what are these doors? So this is exciting to hear both of you on that.
Yeah, I never thought that I'd be in graduate studies, let alone completing my PhD and having the Vanier Scholar. So it's definitely, I thought maybe a diploma would be sufficient for my field of study, but clearly there's more than that in my pathway. So
that's wonderful. So you mentioned your research focus on developing modular housing in northern Indigenous communities. Can you tell us a little bit more about that?
Yeah, so as I'm sure Dr. Elshaer mentioned, that there's a major housing shortage and overcrowding in these Indigenous communities, which leads to moisture buildup and mold and asbestos, or just mold. So when this occurs in the housing, structural integrity is not sufficient, and health is poor in these communities. So we're looking at a modular housing solution which can be lightweight, durable, and resilient to these ongoing extreme climates, such as extreme winds and cold climates in these remote regions. So we're looking at a lightweight structure that can be designed by 1 or 2 people, can be transported there, which can be cost effective. Again, back to being resilient to these extreme climates. And yeah, there's a lot to explain about this topic, but with what I'm currently conducting right now, we're looking at a code compliant solution that can be cost effective and, again, resilient to these extreme climates as previously mentioned. So,
you know, in previous discussion, I think one of the things that needs to be thought of is, so, you know, that you quite often need light materials because of transportation issues and supply chains. But on the other hand, you need them to be strong enough so they don't blow away and have that kind of resilience. So I guess that's where the real balance comes into effect, correct?
We have a few students in our research group that are looking at a connection that can be completely rigid to these extreme climates. So when you design for a modified module and then connect it with this rigid connection, then it can be durable for these extreme climates. And again, going back to what Dr. Elshaer mentioned about the cold climates and heat, where we also have another student doing thermal insulation for these modules. So
you do really work with the communities, and you mentioned about your own background. What do you think is the most rewarding part about this kind of work for you?
Yeah, so that's a very good question. The most rewarding part about this is that being connected with these communities is that we can conduct our research that is suitable for these exact people in those communities. So it's not just making an overall design or structure that can be suitable for majority of the regions, but specifically focusing on that specific region or that specific community or that specific family that wants a modular house, and that we can connect with them one-on-one. So then we can get their cultural inputs, we can get their needs that they want for their own housing, as well as be culturatively appropriate and effective for these extreme climates that we're looking into.
That's great. Yeah. Okay, we're going to take another short break and be right back to continue our discussions with Ahmed and meet another member of his research team. Thanks a lot.
Thank you very much.
Thank you.
So now we're joined by Dr. Ahmed Elshaer again and his postdoctoral fellow, Dr. Magdy Alanani, who discuss some of the other innovative research that's taking place at SWERL. So, thank you for joining us, Magdy. I'm going to start with you. Can you tell us a little bit about your educational background and how long you've been working at Lakehead?
Thank you, Dr. Andrew, for the invitation today. So basically, I started my academic journey from the bachelor degree. It was at the British University in Egypt, and the program was quite unique because we have been doing a collaboration with the Loughborough University in UK. So what was really specific on my, or special about my program is the graduation projects. So I have to do 2 graduation projects. One is a design and another one is research. And that's the first time to establish research project work on artificial neural networks, controller for like seismic actions and earthquakes. And then I moved towards getting more specialized into structural engineering, getting my master's degree from Cairo University, one of the prestigious universities in Egypt. And then I decided that I have to delve deeper into research, and I decided to join SWERL for the PhD program. And for your second question, which is about how long I have been in Lakehead, so it was basically 4 years, PhD and postdoc.
Okay, that's great. That's wonderful. So you mentioned about AI and how it's working there and the numerical methods. Can you tell us a little bit more about that?
Yeah, sure. So my research project is about trying to develop a structural optimization framework for tall buildings using AI. So basically, if we checked about the design process, the conventional design process that we go through, it's typically go through like iterations of trial and error based just on the experience of engineers and architects. And this is basically a time-consuming process, and it doesn't guarantee reaching an optimal solution. And by optimal solution, in the early stage that we are trying to find exactly where to put our structure system, what is the structural system, and where to allocate our columns, beams, and walls, which is basically the core of resisting the lateral loads that we will be having on our structures. So this kind of process is really time consuming, and what I'm trying to do was including the AI to streamline the process. So AI, probably you can explain it better than me as a mathematician, but it's in simple words, we can say it's like having a brain inside a computer, or giving the computer a brain that can recognize patterns, learn by itself, and the good thing about it that it's much faster compared to the typical programs that we have, and it can form a relationship between the data that we give it to the computer based on predefined algorithms. So using this capabilities of how fast it is as an AI system, what we will be doing is we have developed an artificial neural network model. And by neural network models, which is type of an AI or machine learning models, and using its computational capabilities to predict the structural behavior. So instead of trying every proposal for the layout that we decide based on engineers and architects, now we are trying to do it really quick. So we can investigate, or we can test thousands of possible solutions in minutes. And that, using like an appropriate optimization algorithm, we can reach, or we can yield an optimal solution for our structures. And using that way, we are now capable of reducing the cost for the structure, which is the basic theme of my research, and also reducing the amount of materials that we are using. And by the way, these amount of materials are responsible for carbon emissions. Construction industry by itself is just responsible for almost 40% of the carbon emissions. So by trying to reduce all of these, we are trying to tackle multiple problems in just using this approach.
Okay. You know, we hear a lot about AI and people's apprehensions, but you know, to me, in essence, it's just a tool for increasing productivity.
Exactly.
Yeah.
I totally agree with you. Yeah.
Ahmed, we're going to turn to you before we finish off here. Are there any funders or partners you'd really like to give some acknowledgement? You have a large team to support, and I wanted to quickly ask you, working in a team, how is that? What's your experience? I mean, yeah.
Oh, yeah. So working in a team is really an interesting experience, having diversity, like different backgrounds, the interdisciplinary theme for our project, because we are trying to achieve sustainable housing, reshaping the future of housing that we have. You know, currently the whole world is facing a housing problem. Not only Canada, but for example, the Canadian government has decided to push forward to provide 3.8 million units just before 2030. So with this, in order to achieve such an approach, you have to have like kind of a diverse background. So for our research group, we are working on wind engineering, we're working on a structural engineering, structural analysis, and also the thermal behavior of our houses. We are taking it into consideration. And if you look about the experience that we have within the group itself, so we have people that are working on developing AI models like what I'm doing, and other students are working on the wind analysis, doing wind tunnel analysis. Different students are having like the capability to, within their network, the capability to deal with indigenous communities. So we are having a very diverse and inclusive approach toward solving what we are looking for.
That's great. So briefly again, sorry to rush you, just maybe acknowledgements from funders or partners. Supporting a team like this requires support.
That's true, that's true. So I will have to start with acknowledging my team, like my students, like they are the unsung heroes of this system. So I'm very proud of them, and I'm I have so much respect to them. Then going to the funding agencies, like this work is funded by NSERC, MITAX, NOHFC, as well as the government of Ontario. So there is multiple funding agencies, like in terms of the federal, at the federal level. Also in terms of private sector, we have I2R Systems, H&W Engineering, as well as RWDI is one of our collaborators, and from here, from Thunder Bay, we have Coastal Steel. They are one of the collaborators that we have here on town.
We're going to finish off there and say thank you very much for joining us for another edition of Research Matters. And until next time, wishing you all the best. Thank you.